Antarctica's hidden volcano has been melting ice from below for 2,000 years, and scientists just found the proof. Think about that for a second. We have been watching Antarctica from space, measuring it, studying it, warning the world about it. And this whole time, buried beneath nearly 2 miles of solid ice, something has been burning. Not for decades, not for centuries, for 2,000 years. Silent, hidden, invisible, working from the inside out, in total darkness, in a place no human has ever stood. And here's the part that should terrify you. This is not a climate change story. Not yet. This is a story about what the Earth itself has been quietly doing long before the first factory ever burned a single drop of fossil fuel. A volcano that erupted around the time of the Roman Empire and never, truly, stopped. So the real question is this: if the ground beneath the world's most important ice sheet has been on fire for 2,000 years, how much time do we actually have left? To understand what is happening beneath Antarctica right now, you have to go back 2,000 years. Not to a laboratory, not to a climate summit, to a moment of pure geological violence, buried so deep in history that no human being alive at the time could have known what was being set in motion. The year is roughly 325 years before the Common Era. The Roman Empire is expanding across Europe. The Great Wall of China is under construction. And in a remote corner of what we now call West Antarctica, beneath a mountain range known as the Hudson Mountains, the Earth tears itself open. The eruption is not small, not quiet, not local. It is the single largest volcanic event on the Antarctic continent in 10,000 years. A column of ash and molten rock explodes 12 kilometers straight up into the atmosphere. 12 kilometers. That is nearly 40,000 feet, higher than most commercial aircraft fly. The heat is so concentrated, so violent, that it does something almost impossible to picture. It punches a hole directly through the ice sheet above it. Not a crack, not a fissure, a cavity, blasted through miles of compressed frozen water by the sheer force of an explosion happening beneath it. Ash and volcanic material scatter across the entire continent, carried by winds high in the atmosphere, before falling slowly back to Earth and settling into the surface of the ice. And then, the ice closes over it. The ash does not disappear. It freezes in place, locked inside the ice like a fly trapped in amber, preserved perfectly in a single layer of geological time. The eruption ends. The column of fire dies down. The hole in the ice refreezes. And for the next 2,000 years, the world forgets that any of this ever happened. Fast forward to the 1990s. Ice researchers are drilling deep cores into Antarctica at locations called Sipel Dome and Bird Station. These are not dramatic places. They are research outposts, cold and remote, where scientists spend months pulling up thin cylinders of ancient ice from the ground and reading them like history books. Each layer is a year. Each band of trapped air tells you what the atmosphere contained. Each particle of dust or ash points back to a specific event in the Earth's past. And then, buried deep in those cores, the scientists find something that should not be there. A thick layer of tephra, volcanic ash fused with rock fragments, hundreds of kilometers from the nearest mountain range. The layer is too thick to be a trace, too consistent to be contamination. And when the scientists analyze the chemical composition of those ash particles, they find a fingerprint. Not a general volcanic signature, a specific one, matching only one place on the entire continent, the Hudson Mountains, nowhere else, no other source. The scientists are holding physical proof of an eruption that happened in total darkness, beneath miles of ice, 2,000 years before they were born. Not a theory, not a model. Evidence, frozen, waiting, patient. But here is where the story refuses to stay in the past. In the early 2000s, seismic monitoring stations deployed across West Antarctica started picking up something strange. Earthquake patterns. Tremors. Signals in the rock beneath the Hudson Mountains region suggesting that the ground below is still moving, still shifting, still restless. The kind of seismic activity that does not come from settling rock. It comes from magma, from heat that has not finished moving. Then the water samples arrive. Scientists collecting water from the Pine Island Glacier region analyze them for helium isotope ratios, specifically the ratio of helium-3 to helium-4. This matters because these two forms of helium behave differently depending on where they come from. Surface water has a predictable ratio, ocean water has a predictable ratio, and atmospheric sources have a predictable ratio. But water that has been in contact with heat rising from deep inside the earth, from a magma chamber, from volcanic rock still connected to the mantle, has a completely different signature. Enriched, unmistakable, impossible to fake, and impossible to mistake. The water samples from Pine Island do not look like surface meltwater. They do not look like ocean intrusion. They look like volcanic heat, rising from the crust, from the interior, from a source buried beneath the ice that is still generating energy 2,000 years after the original eruption. The volcano never cooled down, not in the way a campfire cools when the last log burns out, not in the way a furnace goes cold when the fuel runs out. The Hudson Mountains eruption was not the end, it was the ignition. What came after was slower, quieter, invisible to anyone not specifically looking for it, but continuous, relentless, a persistent transfer of heat from the Earth's interior into the ice above, happening every hour of every day, in the dark, beneath 2 miles of ice, for 20 centuries, without interruption. And here is the thing about heat that builds slowly in a place where nothing can escape. It does not disappear. It accumulates. It finds its way into the system, layer by layer, degree by degree, until the effects become impossible to ignore. Scientists studying the surface of the ice today are watching glaciers accelerate and ice shelves collapse and meltwater volumes increase in ways that atmospheric warming alone does not fully explain. Something else is contributing. Something from below. Something that has been there the whole time. But here is what nobody told you. The Hudson Mountains volcano is not working alone. And the mechanism by which it is destabilizing the ice above it is far more dangerous than simple heat. The real threat is what that heat creates when it reaches the one place in the entire ice sheet where it can do the most damage. The ice does not melt the way you think it does. When most people picture Antarctic ice melting, they picture sunlight, warming air, temperatures creeping above freezing, softening the surface from the top down, the way a block of ice left on a kitchen counter slowly turns to a puddle. That kind of melting is visible, measurable. It happens at the surface where satellites can track it, and scientists can monitor it, and climate models can account for it. Volcanic heat does not work that way, not even close. Volcanic heat does not come from above. It comes from below, rising through the bedrock, concentrating at the single most critical point in the entire structure of an ice sheet, the boundary between the bottom of the ice and the rock beneath it. That boundary is called the ice-bedrock interface, and it is the most important few inches in Antarctica, because that is where friction lives. That is the grip, the lock, the reason a glacier that weighs billions of tons stays in place instead of sliding toward the ocean like a block of ice on a wet glass table. Volcanic heat arrives at that boundary in total darkness, in a place where the temperature above is always below freezing and surface conditions are irrelevant. And when heat rises into the base of the ice at that location, the meltwater it creates cannot refreeze. There is no cold season at the bottom of an ice sheet. There is no winter at the ice bedrock boundary. The meltwater pools. It seeps into channels along the rock. It spreads into cavities in the bedrock. It builds. And as it builds, it does one thing that changes everything. It lubricates. Reduce the friction between a glacier and its bed, even slightly, and a glacier that has been locked in position for centuries begins to move. Not shuffle, not creep, accelerate. And acceleration does not stay contained. The instability spreads to adjacent ice streams. Neighboring glaciers begin to move faster. The system becomes dynamic, interconnected, and increasingly impossible to predict. One melting point beneath one glacier is not just one melting point. It is a trigger in a system where everything is connected. In June of 2018, a team of researchers published a study in the journal Nature Communications that turned this mechanism from a theory into a measured, documented chemical fact. The lead researcher was Bryce Luce, a chemical oceanographer at the University of Rhode Island. His team conducted an expedition to the Pine Island ice shelf, one of the fastest melting regions in all of Antarctica, and collected water samples from beneath the ice shelf cavity. Then they did something unusual. They analyzed those samples for noble gases: helium, xenon, argon. Noble gases do not react with anything. They do not change. They do not interact with the water carrying them. They are tracers, chemical fingerprints that record exactly where water has been and what it has traveled through. The helium isotope ratios told the story. Specifically, the ratio of helium-3 to helium-4 in those water samples was enriched in a way that has only one explanation: heat from the Earth's interior. Mantle-derived helium does not appear in water unless volcanic activity is actively pushing energy up through the crust from below. The signature was not from surface melt, not from ocean warming, not from atmospheric temperature changes. It was coming from beneath the grounded ice upstream, from magma, from a volcanic heat source buried in the crust, still connected, still active, still feeding energy into the base of the Pine Island system. And when the team calculated the heat output, the number was staggering: approximately 2,500 megawatts. That number needs a physical anchor. The Grimsvatn volcano in Iceland, one of the most powerful and consistently active volcanoes on the surface of this planet, a volcano that has shut down European air travel when it erupts, produces roughly 2,500 megawatts of heat. Scientists discovered that a hidden, invisible, subglacial volcano buried beneath the Antarctic ice sheet is operating at essentially the same power output as one of Iceland's most dangerous surface volcanoes. Not similar, nearly identical. If that just stopped you cold, every subscriber is automatically entered in our monthly giveaway for a branded hoodie. Details in the description. But the Hudson Mountains are not alone down there, not even close. Using aeromagnetic surveys and advanced magnetometry, technology that scans through miles of ice to map what lies beneath, researchers have now identified at least 138 distinct volcanoes buried under the West Antarctic ice sheet. 138. Most of them were completely unknown until recently. They form an underground archipelago scattered across the deep basins beneath the continent, concentrated in the very region where the ice sheet is most vulnerable. Not all of them are currently active. Not all of them are erupting. But their presence reveals something that changes the entire picture. This is not a single hotspot. This is a geologically restless zone sitting directly beneath the ice sheet that holds the most consequential frozen water on Earth. And then the drilling data arrived. The WISARD program, the Whillans Ice Stream Subglacial Access Research Drilling Project, drilled through the ice to subglacial Lake Whillans and deployed instruments to measure geothermal heat flux directly from the bedrock. The result was 285 milliwatts per square meter. Regional geological models had predicted somewhere between 60 and 115. The measured value was 3 to 4 times higher than expected. Confirmed. Repeated. Not a single anomaly at one location. Multiple sites. The same story everywhere the instruments went. The heat is real. It is enormous. It is spread across the entire foundation of West Antarctica. But here is what nobody told you. The most dangerous part of this story is not what that heat is doing right now. It is what happens to all of that underground fire as the ice pressing down on top of it starts to disappear. 4,000 simulations. That is how many times a team of researchers ran their computer models in 2024, trying to understand what happens when the ice above those buried volcanoes starts to disappear. They fed the models different scenarios, different rates of ice loss, different timelines, different combinations of atmospheric warming and ocean heat. And across all 4,000 runs, the same pattern kept emerging, the same mechanism, the same loop. And the results described something that had been largely missing from every major ice sheet stability model that came before it. Here is the mechanism. Pay close attention, because this is the part that keeps glaciologists awake at night. As the ice sheet loses mass from above, from warming air, from warming oceans eating at the ice shelves from the coast, the total weight pressing down on the rock below decreases. This process has a name: isostatic unloading. It sounds technical, but the physics are straightforward. Imagine pressing your hand down hard on a sponge full of water. The pressure keeps the water contained. Now slowly lift your hand. The pressure drops. The sponge expands. The water moves. Now replace the sponge with a magma chamber buried miles beneath the surface of the Earth, and replace your hand with 2 miles of ice weighing billions of tons. As that ice melts and that weight lifts, the magma below wants to expand. Expansion builds internal pressure. Pressure pushes against the walls of the chamber. Stress accumulates in the surrounding rock. And when that stress exceeds the strength of the rock containing it, the rock fractures. The chamber breaches. The volcano erupts. More eruption means more heat rising into the base of the ice. More heat at the base of the ice means more meltwater. More meltwater means more lubrication at the ice bedrock boundary. More lubrication means faster glacier movement toward the ocean. More ice reaching the ocean means more ice mass lost from the sheet. Less ice mass means less weight pressing down on the magma chambers below. Less weight means more expansion. More expansion means more eruptions. The loop feeds itself. The researchers called it a feedback cascade. Each cycle adds energy to a system that is already in motion. Each eruption accelerates the next one. The timescale they identified was not thousands of years, not even a full millennium, hundreds of years. In geological time, that is not slow. That is not gradual. In geological time, hundreds of years is a flashpoint. It is the blink of an eye. It is faster than the Roman Empire rose and fell. Faster than a single civilization has time to adapt. And here is the part that is no longer theoretical. Right now, today, from space, the evidence is already visible. The Pine Island Glacier is not behaving the way it should. Over the past 2 decades, its flow velocity has measurably increased. The rate of ice loss has doubled. The Thwaites Glacier, sitting directly adjacent to Pine Island, the one scientists have quietly started calling the Doomsday Glacier, is collapsing faster than even the most pessimistic climate projections predicted. Something is driving that acceleration beyond what the atmospheric models fully account for. The ocean warming, the greenhouse gases, the surface temperature increases. All of that is real, and all of that is contributing. But the numbers do not add up cleanly. There is excess acceleration. There is instability that the surface models do not entirely explain. The volcanic heat is a wild card, not the primary driver. Climate change holds that position, and nothing in this story changes that. But a wild card in a system already under stress does not need to be the primary driver to be catastrophic. A multiplier does not need to start the fire. It only needs to make it burn faster. And faster, in this context, means something the human mind struggles to fully absorb. The West Antarctic ice sheet contains enough water to raise global sea levels by 15 meters. 15. That is just under 50 feet of additional water distributed across every ocean on Earth. Not in the deep water far from shore. on the coastlines, in the harbors, in the streets. A city like Miami sits at an average elevation of less than 2 meters above sea level. New York, London, Shanghai, Mumbai, all of them transformed, not damaged, not inconvenienced, partially submerged, permanently. The kind of change that does not reverse on any timescale that matters to a human civilization. Slow is a relative term when the destination is 50 feet of sea level rise. And if stories like this remind you that the most dangerous forces on Earth arrive without warning, without announcements, working silently beneath the surface for centuries before anyone notices, grab your free disaster preparedness toolkit. The link is in the description. Scientists cannot drill through 2 miles of ice at thousands of locations across a continent the size of the United States. The logistics are impossible. The cost is impossible. What they can do is watch. They track glacier velocity from space using radar. They measure meltwater plumes visible in satellite imagery. They study the rate at which ice shelves are thinning year over year. And every metric they are watching is moving in the wrong direction. Faster, more unstable, less predictable than the year before. The volcano that erupted beneath Antarctica around the time of the Roman Empire is still awake. Right now, as you watch this, water is pooling in subglacial cavities in the dark. Pressure is building in magma chambers miles beneath the surface. Heat is rising through the crust, reaching the base of the ice, doing the slow, patient, relentless work it has been doing for 2,000 years. We do not know when the next major eruption will occur. We do not know exactly how fast the feedback loop will accelerate. We do not know whether the ice sheet will find a new equilibrium or cross the line beyond which collapse becomes unstoppable. But the ground is on fire. It has been for 2,000 years, and the ice above it is running out of time.